So in our previous video, we talked about the estimation of the Poisson arrival rate using a data collected from the Poisson lambda distribution. So what we have talked about is we have the data set, an IID data set from a Poisson lambda distribution, and we want to estimate lambda. An estimator that we came up with is based on this knowledge about the Poisson distribution. For the Poisson distribution with arrival rate lambda, expected value of x expected value of x is equal to lambda. We can use the sample analog principle to estimate the expectation, and the expectation equals lambda. Sample analog principle, and this equation suggests the following estimator. That is the sample average of x based on our IID sample. As I said, there may be many different estimators based on the sample analog principle. Let's look at some of the other estimators. For Poisson distribution, recall that the probability mass function of the Poisson distribution at value x equals x factorial and lambda to the power x times exponential minus lambda. For x, that is 0 or positive integers. So that is the probability mass function for the Poisson distribution. And from that probability mass function, we know probability that x equals 0 equals exponential minus lambda. In the previous video, we also talked about how to estimate the probability that x equals 0. We can estimate the probability that x equals 0 by the frequency that you had no fish on a trip among your 100 trips. So estimate this with the sample average of the dummy variable for the event x equals 0. So this is the sample probability, sample frequency that you catch no fish. That is a sample analog estimator for the population probability that you catch no fish on a trip. This sample average is an estimator, sample analog estimator of the population expectation for the dummy variable. So in the previous video, we talked about this. Now, knowing this relationship and using this estimator for the left-hand side, we can come up with a different sample analog estimator for lambda. So lambda equals minus of logarithm. This is logarithm with base e, the natural logarithm, minus logarithm px equals 0. So the sample analog principle And this equation suggests the estimator lambda 0 hat, that is minus natural logarithm, the frequency of x equals 0. So this is also an estimator for lambda that's based on the sample analog principle. It's based on the sample analog principle in this equation. In fact, we can come up with even more sample analog motivated estimators for lambda in the Poisson case. So let's say the third estimator, let's say this is the first and this is the second and the third estimator. Recall that the variance of the Poisson lambda random variable also equals lambda. And so if x follows the Poisson lambda distribution, then the variance of x also equals lambda. And the variance of x equals expected value of x minus e of x squared. A simple estimator based on this variance formula is obtained by simply replacing each of these expectations by sample average. So that is the first sample analog motivated estimator based on this relationship, that variance of x equals lambda. Another estimator you may have seen if you have taken statistics course. So this is lambda hat v2. It is almost the same as lambda hat v, except that it is divided by n minus 1 instead of n. So the reason for this adjustments is to make, the purpose of this adjustment is to make this estimator an unbiased estimator of the population variance. So we can show expected value of this adjusted version equals the variance of x, while the expectation of the unadjusted version is slightly smaller than the variance. Now we have four different kinds of estimators, for the same parameter, and all of them are motivated from the sample analog principle. It's just that the equation that we use is different when we apply the sample analog principle. So how do we compare all these sample analog principle motivated estimators? So we have talked about some of the criterions we can use to compare estimators. One is bias, which is expectation minus the true value. The other is variance. So the smaller the bias, the better, and the smaller the variance, the better. And there is another criterion to compare estimators, which is called mean squared error. that combines both bias and variance. The mean squared error, abbreviated into MSE, it is the expected value of the squared error. So the error is the difference between the estimator and the true value. So whenever the estimator is not equal to the true value, it's making an error. And the size of the error is measured by the square of this error, because both positive and negative errors are undesirable. So the size of the error is reasonably measured by the square of it. And then because this is a random quantity, we take an expectation to summarize the information in this random quantity. So once we take expectation, that's the mean squared error. That's how much error the estimator makes on average. We can show that mean squared error is a combination of the bias and the variance. In fact, it's mathematically equal to the square of the bias plus the variance. How do we show that? You can start with the MSE formula. MSE equals expected value of this error squared. This error, we can turn this error into the sum of these two errors. One error is the difference between lambda hat and expectation of lambda hat. The other is expectation of lambda hat and lambda. So these two sides are equal because to obtain the right-hand side, what we did is only to subtract E lambda hat and then add the same thing back. But by doing that, we create two different terms. Now, the next step is simply to write out the square. Write out the square. The square is the square of the first term. Square of the first term. And plus the square of the second term. And plus a cross product term. A cross term. Okay, the cross term is 2 times the product of the two terms. The expectation of the sum of these three terms equals the sum of the three expectations. For the first expectation, which is right expectation of this term, expectation of lambda hat minus E lambda squared. For the second term, we should notice that this is a non-random term. This term is a constant. Because expectation is a constant and lambda, the parameter value, is also a constant. So expectation of this constant equals the constant itself. For the cross term, we can notice that this is a constant, 2 times a random variable times a constant. So both 2 and this term are constants. When they are constants, they can be factored out of the expectation. So when you consider the expectation of this, you can factor this constant out of the expectation. So you bring that out of the expectation, write it in front of the expectation. And what's left inside the expectation is the expectation of this random term. Now, going from here to the third line, we observe that this first term is nothing but the variance of lambda hat. So that's the definition equation for the variance of lambda hat. That's variance of lambda hat. And this is the bias squared by the definition of bias. And this term, you observe this expectation. So that equals expectation of lambda hat minus expectation of expectation lambda hat. But expectation of expectation lambda hat is expectation of lambda hat because expectation of lambda hat itself is non-random. When you take expectation of a non-random quantity, you get the quantity itself. So therefore, that is 0. So that proves mean squared error equals variance plus bias squared. So we have these three criterions to compare the estimators on, but how do we compute those criterions? It is easy to compute the bias and variance and mean square error for some of the estimators, but not for all. In fact, for the estimator that is based on zero frequency, for this estimator, lambda hat 0, it is quite impossible to calculate the bias and the variance analytically because you have a nonlinear function minus logarithm around the sample average. It's not quite possible to analytically calculate the bias and the variance. For the estimator that is based on variance, it is possible with a lot of algebra to calculate the bias and the variance of this, but it's complicated. So maybe we should look for a way to compare the bias, variance, and mean squared error without explicitly calculating them, without analytically calculating them. What is the solution to this problem? The solution is Monte Carlo simulation. Monte Carlo simulation is a tool that we can use with the help of our computer, and it's the basis for Monte Carlo simulation is super simple. The basic is the frequentist point of view of probability. So basically, what we want to do is to approximate this expectation using sample average of a large sample of lambda hat, of a very large sample of lambda hat, so that the approximation is good. And we approximate every expectation using sample average from a very large random sample of lambda hat of the estimator. But of course, this random sample of lambda hat is not the random sample that you have used to compute lambda hat. To generate these large random samples of the estimator, you need to generate your sample of size n many times and independently. You need to generate m number of size n samples. What do we mean by m number of independent size n samples? We can go back to the fishing example. Now suppose you, this is you, person 1 is you. You go to the pond and fish for 100 days, and you're gonna get a random sample of size 100. But that only gives you one value, one realization for one estimator. One realization for each estimator. And that is not useful for calculating the expectation of this estimator. In order to get many samples of the estimator, you're going to have to hire many people to do what you do, to go to random points on the pond and fish for 30 minutes every day for 100 days. To hire many copies of yourself and do what you do for 100 days. And each of them is going to collect a sample of size n. And from their sample, they're going to calculate a realization of the estimator. Then when you pull all of these estimators, all of the realizations of the estimators together, you're going to get a random sample of the estimator. So this lambda 1, lambda 2, lambda m collected by your m people, the army of m people fishing on the pond, will be m random draws from the distribution of your estimator lambda hat. Then you can use the sample average to approximate the expectation, And based on these M observations, you can use the sample variance, you can use the adjusted version or the unadjusted version. When the M is big, those two are not very different. So you can use this sample variance to approximate the population variance of the estimator. There is a subtle difference between the pond example and Monte Carlo simulations. In Monte Carlo simulations, you're going to have to fix a lambda value. In a pond example, you do not know the lambda value. But in Monte Carlo simulation, you are going to choose a true lambda value. And I'm going to choose lambda equals 1. You could choose any other value, 0.5 or 2 or 4. You fix this lambda value, so you have a fixed Poisson distribution. Then from this fixed Poisson distribution, you can generate your m different random samples of size n. From each random sample, you can calculate your estimators. Then you get m independent copies of those estimators. Then you can use this sample analog principle to evaluate their bias, their variance, and mean squared error. To gain some concrete idea of how that's going to be done, let me show you an Excel exercise. Let me stop the sharing for this one and share my Excel here. So in order to do the Monte Carlo simulation, the first thing is to decide what's the sample size you want, the sample size that you base your estimator on. And also, you want to decide how many samples you want. So here, what I want is n equals 100. I want the sample size to be 100. And I want m, the number of random samples to use to evaluate the estimator. I want that to be a large number, let's say 1,000. And I choose my true value of lambda to be 1. You can choose other numbers. And then I want to generate my data. I want to generate 1,000 samples of size n. Each sample of size n, each sample of size 100 is put on a row with 100 cells. For each row is one random sample from which I can calculate an estimator. And then my Monte Carlo is going to need 1,000 rows because I need 1,000 copies of that random sample of size 100. So I will generate an 1,000 by 100 table. In each cell of the table, there is a Poisson 1 random variable. So how do we generate that? I will use the data analysis tool in Excel. The data analysis tool you can see right here by clicking on data, the data menu. Just in case that in your Excel you don't see this, it might be because you need to choose an add-on. To choose the add-on, you select File, and in File, you select More, and then you go to Options. In Options, you click on Add-ins. In the add-in list, you want to make sure that the analysis tool pack is in the active part, not the inactive part of add-ins. If it's in the inactive part, you're going to select it and move it to the active part. I believe you can do that by clicking on OK after selecting this one. So I'm not going to do anything because I have already added analysis tool pack. And I already have this data analysis button. I'll click on this button. Then you have this menu of options. In this menu of options, you want to choose random number generation. Once you click on that, you have this dialog. In this dialog, you put in the number of variables, which is the number of columns. In our example, this is your sample size. And here I put n equals 100. And the second number, this number of random numbers, is the number of random samples. Okay, so the first one is sample size, number of observations in each sample, and the second one is the number of samples, which correspond to the number of independent copies of the estimators. So that's our M, which is 1,000. So I choose 1,000 here. And from which distribution do you want to generate the random number? We want to generate from the Poisson distribution. So I'm going to choose Poisson from this drop-down menu. Here I put on my true value of lambda. I put 1. You could try different numbers. And I'm not going to mess with the other options. So I click OK. So actually, I want the output range to start from A2. Let me see whether that works. So it takes a minute because it's a huge matrix. Yeah, so it works. So from the second row on, so this is the first random sample of size n. This is the second random sample of size n. There will be 1,000 of them. So for each random sample, I'm going to calculate the estimators. The first estimator is lambda hat E. So that's the expectation-based estimator, which is quite simple. It is the average of all the x in the sample. All the x in the sample are in the cells A1 to A2, actually, in the second row, A2 to CV2. So this is the lambda hat E for the first sample. You can copy that formula to the second sample and third sample and so on. A fast way to do that is to move your cursor to the lower right corner of this cell. And when it becomes a bolt cross, double click your mouse, double click, and all of the cells are filled with the same formula. So all of these are the estimator, the expectation-based estimator for the corresponding sample. So that's the first estimator. Now let's calculate the second estimator, which is lambda hat 0. So that is the zero frequency estimator, the frequency of zeros. That is based on the frequency of zeros. And that estimator is a little more complicated. It's minus logarithm. In Excel, if you want a natural logarithm, you want to specify the base to be exponential 1. So what is the quantity that we want to take a logarithm for? That is the frequency of zeros, right? So that's the frequency of zeros, sample average of the dummy variable indicating x equals 0. So the frequency of zeros in Excel can be obtained by this command, this function, COUNTIF. Let's count the cells that equals a value given by you, which is 0 in this case. I will count if first I'm gonna specify the range, which is A2 to CV2, and then I count all the cells in this range that are equal 0. The count of zeros divided by the total count of the cells, which is 100. That is the frequency of zeros. And that is the estimator based on the frequency of zeros. I then double click this bolt cross to fill in all the rows. Now the third estimator is the first variance-based estimator. So that's lambda hat V, which is in Excel is variance.p, the unadjusted variance estimator. Unadjusted variance estimator. So that is variance P A2 to CV2. And the fourth column here, the fourth estimator is the adjusted variance estimator, lambda hat V2. So for that one, we use variance.s. And I'm going to also double click to fill up all the cells. Now I want to go to the bottom of the table to calculate the bias and variance and mean squared errors. So let's say this is bias, this is variance, and this is mean squared error. I want to label each one by this is E, expectation based. Sorry, this is expectation based, and this is zero frequency based, and this variance based, and this variance based too. So to get the bias, I simply take the average of the estimator value over these 1,000 draws. 1,000 draws is CW2 to CW 1001. I start from CW2 because the first row is something else. It's the title. I set it up this way. So that's the average. The average just approximates the expectation. Average minus 1 approximates the bias. 1 is the true value. So that's the approximate bias of the expectation-based estimator. Notice that this bias is not zero, even though we have proved this estimator should be unbiased. It is not zero because we only have 1,000 random samples, not infinite number of samples. But it's quite small. So our error is not that big. And I'm gonna drag this bolt cross horizontally to fill in these other 3 cells, and these are going to be the bias for the other estimators. So comparing the estimators, you find that the bias of this bias, the bias of this, the fourth one, let's look at the fourth one because this is also supposed to be an unbiased estimator. This unbiased estimator, at least in this particular realization, it looks like it's quite small. It's close to zero. It's not zero, even though it's proved to be unbiased, but it's quite close to zero. It's not exactly zero because we don't have an infinite independent copies of the estimator. We only have 1,000. And these other biases are not big either. So these other estimators don't seem to be super biased either. Maybe that is because the sample size 100 is quite big. And for the variance, let's use the unbiased estimator for the variance, variance.s. The variance is this, and we drag it across to obtain the variance of all of those. Sometimes it's useful to find the standard deviation. Standard deviation is the square root of the variance. The standard deviation is in the same unit as the variable itself. So the standard deviation is kind of in the same unit as bias. When you compare the standard deviation with the bias, you can see that all four estimators don't have a great deal of bias comparing to their variance. So their variance is the more important thing. By comparing the variance or standard deviation, you find the expectation-based estimator has the lowest variance. And it's quite obviously different from the other estimators. Now for mean squared error, it is the bias squared plus the variance. Now once we get the mean squared error of all of those, we find that the mean squared error it's quite close to variance because the bias is quite small. So the mean squared error, by mean squared error, the expectation-based estimator is still the best one, while the others are worse. So it looks like the zero frequency-based estimator is slightly better than the variance-based ones, but the expectation-based estimator is by far the best. It's better than the other estimators. Okay, so that's how you use Monte Carlo simulation to evaluate the bias, variance, standard deviation, and mean squared error of different estimators. You're going to need to specify a true value for your parameter value lambda. Sometimes the relative performance of the estimators are different when you change the true value of your lambda. But in the Poisson case, I'm guessing that it doesn't matter so much. The true value doesn't matter so much. In other models, it might. Okay, so let me go back to my drawing pad to show you a little bit about the intuition or the reason behind the good performance of the expectation-based estimator. So our Monte Carlo simulation tells us that the expectation-based estimator is the best estimator according to all three criteria. This, in fact, is not a coincidence because for Poisson distributions, the expectation-based estimator, which remember it equals the sample average of X. The sample average is the efficient estimator of lambda for Poisson distribution. So this is not the case for all distributions, but for Poisson distribution, this is the case. So it is the efficient estimator. So what does efficiency mean? When is an estimator efficient? Efficiency is actually a quite technical term. It has lots of technical stuff in it in order to define rigorously. But we don't have to go into that. All we need to know is that it has the lowest variance among a large class of estimators, among all regular behaving estimators in large samples. So this estimator has the lowest variance among these regular behaving estimators when the sample size is large enough. So that's roughly speaking what efficiency means. And because it is unbiased, so if it has the lowest variance, it has no bias, so the mean squared error is of course also the lowest. So it is the lowest variance among all regular behaving estimators. So you might be wondering, what is a regular behaving estimator? So that is also a quite technical term, but roughly speaking, regular behaving estimators are estimators that are asymptotically normal. A concept that we will cover. So this asymptotic normality is a concept that we will cover in future videos.